to our colloquium. I'd like to introduce Assistant Soon-to-be Associate Professor Peter Onyisi. Peter is a experimental particle physicist. He'll talk to you about some research at the ATLAS experiment, but he got his bachelor's at the University of Chicago, where he was a winner of the APS's APCR award. And then he went to Cornell for his PhD, where he worked on the CLIO experiment, studying branching fractions of charmed strange mesons, so flavor physics. And after that, he went to the University of Chicago as an Enrico Fermi Fellow to do his postdoctoral work, where, among many things, he was a significant contributor to the discovery of the Higgs boson in the WW channel. And since then, he joined the faculty at the University of Texas, Austin, 6 years ago, 5 years ago?
Well, 2012, so.
In 2012, he's been there. And he's done a number of things. What I think he'll talk to us about a fair amount today is he's led the group that did measurements of the Higgs coupling to top quarks, which is currently one of the most interesting Higgs measurements that we can make right now. And he's additionally the ATLAS experiments data preparation coordinator. And I just want to explain what that is, because it's kind of an opaque term if you're not a member of the experiment. But the data comes off the ATLAS detector in a stream of zeros and ones from a very heterogeneous set of subdetectors. And it's Peter's job to make sure that that gets to the analyzers in a form that they can recognize and search for Higgs bosons. It also requires that we know how much data was taken and what conditions those data were taken and everything. So for the entire 4,000 person collaboration, Peter's in charge of making sure that all works. So without further ado, let him start.
All right, thanks very much, Lauren, and thanks very much for having me. So right up here, I have the LHC page 1, which is a web page that anyone can access, and it gives you information on the current status of the machine. So in fact, very recently, I guess basically a week ago, we had first beam in the machine for this year, and in fact, in principle on Thursday, we might be getting first collisions, although not good for physics ones, so we have to make sure that to filter them out for users. So right now, the LHC machine people are doing various optics things and recommissioning the accelerator for this year. So it's a bit hard to do this. Okay, so here comes the actual talk. All right, so I'm going to talk about top quarks as the new flavor, and of course, we've known about top for quite a while, but since I have a bit of what we call a flavor physics background in my field, I find that it's actually rather hard to escape it, and so I've wound up studying quarks again, except a much heavier one this time. So this is not going to be a full survey of top quark physics. It's really actually going to focus on things that I personally have worked on, and hopefully give you a little bit of a flavor of how we actually do things in this field for people who may not be familiar with particle physics in general. So I'll start off with a little bit of an overview of the standard model of particle physics. So looking at the sort of reductionist paradigm, we keep looking at things that are smaller and smaller, trying to explain the properties of larger things in terms of a smaller subset of components. So we start off with everyday matter. We realize, we have an awful lot of different kinds of materials in the world, but they're all formed chemical combinations of different elements. We ask, well, why do we have the atoms that we have? What explains the regularities of the periodic table? We find that the periodic table arises from quantum mechanics of electronic configurations. You have to put some number of electrons orbiting in a potential. Okay, what explains the kinds of potentials that you have? That comes from nuclei, and we find that nuclei, we have this quantized behavior coming from having protons and neutrons in them, integer numbers of those, and then we find inside those that protons and neutrons themselves are composed of different numbers of more fundamental particles, quarks. And actually, as far as we know, as far as matter particles go, this is where it ends. So we haven't seen anything inside an electron to date, and we've never seen anything inside a quark to date, not for lack of trying. People have certainly tried. So we can actually summarize all the directly known fundamental particles, again, particles that we've not been able to divide in any way, in this little cute pie chart. And we can, it's not enough to know what the content of the world is, you also want to know how they interact with each other. So you want to know the dynamics of it. So you have a Lagrangian here, and you can, actually there's an error in this. So this is something you can get from CERN, and there's actually a flaw in it. So if you spot the flaw, you can pat yourself on the back. So the question that we're really trying to ask and answer is this a complete set of material and forces? And we actually know it can't really be, but this is what we know of. And is this Lagrangian, which again, very, very simplified expression of it, is this what there is to know about the dynamics of these particles? And again, we have reasons to believe that's not the case. So all ordinary matter is actually just composed of these. So looking back at that first slide I showed, we have electrons and then the two quarks inside the protons and neutrons, the up and down quarks. And then it turns out that for reasons unknown, there are heavier versions of these things, so things with the same kind of dynamics, the same charges under different forces, but heavier for some reason. So you can also sort of tell the point at which people stopped trying to come up with Greek names for things and just switched to English. So we have heavier partners of electrons called muons and taus, and then we have up, charm, and top, and then for down, strange, and bottom. So these have a complicated pattern, which I'll come back to a bit later, of exactly of their relationships with each other, and no one really knows where this pattern comes from. On top of that, we've got these hard-to-see neutrinos. So 100 trillion neutrinos from the sun pass through you every second. You don't notice, so that tells you a little bit about how rare their interactions are. And studying the properties of these, which in some sense really are some of the least well-known particles that we have established exist. We don't actually know what their masses are, for example, as opposed to everything else. So this is a major part of the US particle physics program for the future. Then one of the major realizations is that not only is matter composed of particles, but in fact the forces between particles are also particles. So we have the particle of light, or electromagnetism in general, the photon, and given as we are visual animals, a lot of our culture is encoded in electromagnetic interactions. We have the gluon. This is the thing that keeps these up and down quarks actually bound into these objects, protons and neutrons, and not just those, but gives us other kinds of configurations of these quarks. The W and Z, which are a bit more obscure, the most direct relevance they have to us, they mediate radioactive beta decay, the W does, and allows the sun to shine. So the way the sun turns 4 protons into a helium nucleus involves the W. And then in the middle of this, of course, since I like to do Higgs physics, we put the Higgs in the center, obviously, this should be right. So this particle gives mass to the others in this picture. So looking at the dynamics here, we can actually sort of summarize what's going on in these different terms. So we have a term corresponding to the force particles moving. And again, this is highly summarized. This is cramming many, many lines of a thing together. We have the matter-particle motion and its interaction with forces, and they're very tightly coupled together in terms of you don't have an awful lot of flexibility in how this term must be once you've chosen certain underlying mathematical symmetries. We have the matter-particle interactions with the Higgs field, and this is much more free, in fact. We have the Higgs field motion and interaction with the forces, and then we have the Higgs field's self-interaction. So you see the Higgs actually shows up a whole bunch of places in here. So this picture is not at all complete. There are a lot of things that we know are not there. So the big thing is I've said, oh, look at these forces. Well, I haven't mentioned gravity, and since you're all sitting down, I think you believe gravity exists. So there's no verified theory of quantum gravity. There's no dark matter, so or dark energy. So if you look at the universe, you do cosmological measurements, you ask how much stuff is there, how much energy is there in various components, and you use general relativity, you go and measure, count things actually, you find that you don't have enough you certainly don't have enough matter of our kind to explain the amount of matter that we conclude must be in the universe. And we also know that neutrinos don't have the properties that you would need to have for a viable dark matter thing. So it's not just that we have a lot of neutrinos and not just baryons. So basically, we know there must be some kind of dark thing out there. We also know, I mean, even worse than that is that the majority of the energy budget of the universe at this time comes from something that isn't matter at all. It has the property that as the universe expands, there's more of it. So the universe is being inflated by this invisible source of energy. We don't know what that is. In this model as is, there's not enough matter. It doesn't predict, if you start with a universe that doesn't have, that has no net amount of matter versus antimatter, you can't generate enough of an asymmetry to explain how much matter there is now as opposed to antimatter. There's no neutrino masses in this model, although in principle most theorists would say it's an easy bolt-on. So, but we know that there are degrees of freedom beyond the standard model. We know neutrinos have masses. And also a somewhat more theoretical concern, naturalness, in that the parameters of the model regarding the Higgs field seem to be very highly fine-tuned in a way that doesn't seem sensible. So I'll say a little bit about, try and give you an idea of how the Higgs field works in terms of giving masses to things. And the top quark being the most heavy particle that we know of, this is a very strong interaction between the two of them. So this is spontaneous symmetry breaking. If you ask, well, what's the point of this whole thing? This is basically when we talk about electroweak physics, this is what we're talking about. What the fundamental point is, if you look at the weak interaction, so the thing with the W and Z bosons, that's a force, so there are charges involved. The same way that, what determines electric force? Well, you've got electric charges. The weak force, particles that experience the weak force have a weak charge. The thing is, if you actually ask what would happen if I put a mass term in the Lagrangian, just bare, you find that this would actually violate conservation of this charge. And that's a bad thing. We do not like violation of charge conservation. So what we do is we have a fundamental Lagrangian that is invariant, that doesn't violate charge, but we create a vacuum that does. So this is the sort of same principle that you have a ferromagnetic material. It has the ground state of it has all these domains where you have, at low enough temperature, has domains where spins are aligned, and you have a net field, and it picks out a preferred direction, even though the fundamental laws don't have any preferred direction in them, but the ground state has a preferred direction. Same here. Essentially, if you look at the potential that we posit for this Higgs field, and of course this is a supposition. This is not necessarily the full form of the potential. There could be more than one Higgs field, et cetera, but this is the simplest model. Then what you find is that the symmetric situation, where there is no Higgs field, is actually a local maximum of the potential, and that if you want a minimum of the energy, you actually want to be at some value that's not zero. So this drives the so-called vacuum expectation value, in which you actually have, the Higgs field is in lower energy if you have a non-zero field. And given the way this is coupled to the fermions, this vacuum expectation value winds up generating a mass term in the Lagrangian. But it does this at the same time as it generates an interaction of the fermions and some oscillations around this minimum. So the oscillations around this minimum are what we call the Higgs boson. And this says, well, the mass of the particle, which is determined by this constant y, which we call Yukawa coupling, that mass here relates, it not only tells you the mass, that y tells you not only the mass of the particle, but also the strength of the interaction between the particle and the Higgs field. So this is how the top quark gets its mass, and this is why the top quark is expected to interact with the Higgs boson. So there's this wonderful paper, which is actually just past its 50th anniversary, so it's called A Model of Leptons by Steve Weinberg. And if you read it, you sort of read it and say, okay, we're done, it's, this is the answer to everything. So it doesn't have quarks in it, which is, okay, at the time it was not, there were good reasons for not having them there. But as far as the leptons are concerned, it's correct. So when I say flavor physics, I really mean, again, studying the matter sector and its interactions. And in particular, I'm mostly going to talk about this particular thing here, which is the interactions of the matter with the Higgs field. So one more bit of fun theory here, and this is driven a lot of work, including the people here who worked on Babar, so you know all of this. So this issue here that happens, and it happens for both leptons and quarks, so both electrons, muons, taus, neutrinos, and the quarks, is a mismatch between the mass and weak eigenstates. So if you think back at this coffee cup, you basically have matrices here you can diagonalize, but there's no particular reason, relating the different generations of quarks, but there's no particular reason that this diagonalization has to have the same form for both these two terms, and in fact, they don't. So the Higgs interactions and the weak interactions wind up picking out different basis states. So you have this sort of multidimensional states of lepton and quark flavors, and you pick out specific preferred directions in them, but those preferred directions need not be the same for the masses, so the things that are mass eigenstates, and the things that interact with the weak force. So for the standard model, quarks, we use mass basis. So we actually have things where we can go and more or less measure the mass of them. And so it's natural to say, well, the top quark is this thing of charge plus 2/3 and mass 172.5 GeV. So this means that the mass terms in this case conserve flavor, because we define that the flavor are the eigenbasis of the mass. The photon Z and Higgs interactions conserve flavor. That means they don't change one kind of particle into another. So if I have a top quark, it emits a photon, it's still a top quark, will always be. So this means that there's, in our jargon, there's no flavor changing neutral current. So there's nothing that doesn't involve a W that changes the kind of what a particle is. And the W interactions can actually change particles to another, and this mismatch of the basis produces a matrix which is unitary and tells us basically about the overlap of these bases. Leptons, in fact, use the weak interaction basis. So neutrino oscillations are discussed in terms of that. They're conceptually the same thing, except the processes of neutrino oscillations and of the CKM matrix are actually conceptually the same thing, just expressed in slightly different ways. So a brief taste of the sort of thing that has been done in quark flavor physics, which is actually still, for non-top quarks, which is actually still a really interesting field in many ways. Very, very brief taste here. So one thing, of course, to do is to take this matrix and actually probe it and try and measure all the components and test the unitarity. And that's done with this so-called unitarity triangle, amongst other things. Because if you say you find some measurement that should agree with the consensus of all the other experiments and find it disagrees, that might be evidence that something is contaminating your measurement, some kind of new physics. So you would have something inconsistent with a global fit. So what this actually represents is basically three numbers that should add up to, wind up adding up to 0, which is essentially the same as saying that these two columns of this thing should be orthonormal to each other. So they should have, if you take the inner product, they should be 0. So that's what that comes from. Another thing you can try and do is test the universality of lepton couplings. So in the standard model, except for the Higgs, the leptons are treated the same way by the weak interactions. So if I look at a process where, say, this particle, there's a B quark here, it turns into a charm quark. Again, it can only do that by emitting a W in the standard model. Then I should be able to predict that W doesn't really care whether it decays to a tau, a muon, or an electron. For it, those things are all the same. But if I had, say, some kind of extra particle that distinguishes tau from muon from electron, which, for example, could be some extended Higgs boson, then this would violate the expectations from the Standard Model. And in fact, there is a hint so far that this may be happening, in that there's a prediction of the Standard Model in these ratios here of various decays, which should be here, and the combined result from all the experiments is over here. And this is actually quite a significant discrepancy, although no single experiment has yet shown conclusively that there actually is a discrepancy. But this is something to look out for. So this is actually tree, right? So, So the fact is, actually, people have to explain how this is consistent with everything else, given that it should be a fairly important process if it's tree. Yeah. So you don't even have to go to loops for this sort of thing. Okay, so to come back to the top, so I mentioned that there's this relationship between the top and the Higgs and this naturalness problem. So the top quark is very heavy, so it is the heaviest known fundamental particle. That means the top Higgs interaction is very strong, and that means that you have to actually consider quantum corrections. You can't just take first order in perturbation theory. You have to consider higher orders in perturbation theory when computing things, and then you get corrections to the Higgs parameters. And so something like this, where the Higgs boson turns into a top pair and then they turn back into Higgs boson, this can happen on short time scales, no problem. And then you find, well, if I assume that there's, I have new physics that cuts things off at some high momentum scale of this top this top loop, because I, in principle, can have arbitrarily high momentum tops in here. What I find is that there's this correction to one of the Higgs mass parameters that actually scales quadratically with that cutoff choice. So if I chose that to be, say, the quantum gravity scale, this would be 10 to the 32 times the observed value, and you have to somehow cancel 10 to the 32 against 10 to the 32 to get 1. So you really need an extreme cancellation of this bare parameter. Now, I mean, fundamentally, there's no fundamental problem with that, but it seems extremely arbitrary. You would like to have some motivation for that. So this motivates looking at new physics models which cancel the correction in some natural way, or lower the cutoff, or both. So supersymmetry famously introduces particles where you would have a plus sign for a top, you would have a minus sign for these particles, and so naturally these things would cancel. Extra dimensions, for example, can come in and reduce the quantum gravity scale, so the cutoff goes down. Composite Higgs would say, well, again, at some point the Higgs becomes more, a fuzzy thing, and these computations no longer apply. So there's a lot of work that's been done in this direction, motivated by this problem. In some ways, this has really driven most of the work that's been done at the LHC, is trying to find solutions to this. But the bottom line here is that Higgs properties are enormously affected by the top quark interactions. And then here's what I like to call the Doomsday Plot, which asks whether, so if you took the Standard Model to be correct, you say, okay, I forget about all this naturalness stuff, I just take what it is, but then I do just the quantum corrections under those parameters to the Higgs potential. What you find, okay, we're here at some relatively small but non-zero value of the Higgs field. Is our vacuum, and then you look at what happens to the potential, it grows, and then it actually turns down again. So with our current best knowledge, it basically depends on the top mass, or the top Higgs interaction, because that's what gives you the top mass, and the Higgs mass, and you find that actually this turns down, and for our current known values, gives a second minimum that is lower in energy than the one we're in. Now, if you know what this kind of thing implies, that implies there's some probability to tunnel between these two states. If this minimum were significantly lower than where it is, we would have done that already. So we wouldn't be here to talk about it. In fact, we kind of like that situation were that to be true, because then we could say, well, something must be stopping it because we're here. But unfortunately, that we are in this fortunately or unfortunately, the current parameters that we've measured put us in this metastable region. And you can see that a small change of few GeV, giga-electron volts, on the top mass would actually move you from metastability to stability. So measuring the top mass, which again is basically measuring the top Higgs interaction, is clearly a priority in order to understand whether this might mean something. Okay, so questions for the Higgs sector that we're trying to resolve. Basically, the Standard Model has the simplest possible Higgs sector. It's one fundamental doublet of complex valued fields, so 4 degrees of freedom. Is this we don't know if this is actually, if the simplest model is correct. Maybe there might be extra doublet or triplet or something. We don't know that these particles are in fact fundamental, because all other known spinless particles are in fact composited. And we don't actually know that the symmetry breaking potential is what we guess it is. So what you'd expect to see, things like modifications of the interaction strength if the Higgs is actually a composite particle, a composite field. If you had more degrees of freedom, you'd have more particles in the sector, but also you could expect modifications of the interaction strength and these flavor-changing neutral currents to appear. And if the new interactions we don't expect, and if the potential wasn't a quartic, actually self-interactions would be modified. So I'm going to talk about things in blue, modification of the top Higgs interactions, so measuring that directly, and flavor-changing neutral currents, searching for those. So to move to the experiment, the fun side. Okay, so here is a representation of where the LHC runs underground. It's actually sort of order 100 meters underground, so you don't see very much of it on the surface. So here is the runway of Geneva Airport for comparison. Here is the ATLAS experiment where I work. It is conveniently close to a tram line. Here is where the essentially equivalent of ATLAS, our colleagues of the CMS experiment, are. They are not close to a tram line. So this ring, 27 kilometers circumference, more or less, it actually has other experiments on it as well, beyond ATLAS, my experiment, and CMS, the sort of sister experiment to ATLAS. So ELISE is focused on heavy ion collisions, and LHCb actually does very interesting, essentially lower mass quark physics with a different kind of detector design, so they're very complementary to us. So we collide protons that have kinetic energy over 6,500 times their rest mass. So basically all the energy of these things is in their motion. It was first operational in 2009. We saw the Higgs in 2012. And in 2015, we got to near the planned energy of the machine. So here is a person biking between points. So this is actually, there's only so many ways to get into the thing, and if you're trying to get to an intermediate point, you take a bike. So this is very carefully posed at the French-Swiss border underground. This is what the experiment itself, what would look like if you could actually see it all at once, because the geometry of the underground cavern means you can't really. So this is, so here are people for scale standing where they shouldn't be, about 25 meters tall, 44 meters long. It's a very big thing, although most of that is actually air. So we have a fairly compact inner part of the detector, and then a large volume with magnetic fields in order to allow enough lever arm for measuring the particles' trajectory bending in the magnetic fields. So this design a lot of different kinds of detectors where you arrange them in the sort of onion shell pattern, where you do try and do non-invasive measurements first and then more invasive measurements later to try and collect as much information as you can about the trajectories and the properties of all the particles involved. So since computing is a thing I worry about, so here's some facts on that. The early data output of the experiments is order 30 petabytes, and we show no signs of reducing that. Actually, it turns out that the major challenge is not actually reconstructing the data. That you can actually do at CERN. The major challenge turns out to be simulating what we would see. So the problem is, of course, the universe is a very good quantum computer on its own. We're trying to do a lot of simulations of quantum mechanics ourselves, but it's difficult on a digital computer. And then you want to actually see how the detector would experience having a certain kind of interaction occur inside it. So that takes the vast majority of the CPU resources. These are run on the distributed worldwide LHC computing grid, which, as the last time I checked, is 170 sites over the world and about 260,000 real cores running pretty much all the time. Okay, so the general principle of what we do, we take these protons, we collide them, stuff comes out. Well, something happens first, but that something, if we make a Higgs, that thing has a lifetime of about 10 to the minus 22 seconds. If we make a top quark, that's like 5 times 10 to the minus 25. We don't see those things directly. What we see is that these things, they decay into something else, and those things decay. And by the time you get to stuff that has lifetimes of microseconds or later, then we can actually have it move far enough for us to actually see things. So we get some particles out, and in the end, some things are actually detected, and then it's a bit of an interesting jigsaw puzzle to figure out what is consistent with having produced what we saw. So we're looking for the long-lived particles that come from these collisions. So and I talk about why is this interesting? What is qualitatively new about this in terms of making top a new flavor? Well, only 2 accelerators on Earth have ever had enough energy to make top quarks or Higgs bosons. And if you look at sort of this bar chart here, essentially all top quarks that have ever been made on Earth have been made at the LHC. So we have roughly 70 million of them, have produced roughly 17 million of them, and the amount that was number produced at the tevatron much, much, much smaller. So once you have that kind of numbers, you can actually begin to do lots of really detailed investigations that you couldn't do when every top quark was supremely precious. So this is what top quark pair production looks like. So I mentioned, all you see is the remnants that live long enough. So what's happened is we made a T and a T bar, so a top and an anti-top. The top is decayed to a W boson and a B, which is what it does essentially all the time. The anti-top has gone to W and B bar, and in this case, the W is decayed to a muon and a neutrino, and this W has gone to an electron and a neutrino. So what we see in the final state is a muon here, an electron here, and these are recognized by the different patterns of energy deposition in different detectors, where they are able, how far they're able to penetrate. And then we have these 2 bunches of particles that contain quarks, so these hadrons, which we identify as having arisen from B quarks. So we never see quarks on their own, we only see them bunched up in with other quarks, but we're able to tell that these actually came from Bs. And how are we able to do that? Well, it turns out that the B quark lives just long enough for us to be able to see that it flies a macroscopic distance. So if we look at the particles coming out from the collision, so this is the primary vertex, this is where most of the particles are coming from, we see that we have a bunch of particles here that, when reconstructed where they came from, actually come from a point that's displaced. So this fact that something has flown from this collision, from this primary interaction point to here before decaying, gives us something very consistent with the idea that was actually the time it took for a B quark to decay. So we collect data at a fast clip. At the design luminosity, which is expressed in these weird units of area per second, we actually produce 8 top pairs per second, and we exceed that. So this year we expect to maximal run at twice that. So we routinely run higher than the design. So this is data accumulated per year. Again, some units, don't worry about it, but higher is better. And the best year we've had for LHC operations was in fact last year, and we're hoping to do as well or better this year. And this is something we've been doing at UT, is actually validating that the luminosity measurement is stable with time using physics processes that we can actually control. So that's fun. So while collecting data, we're actually sensitive to about 93% of the delivered data. We can't actually record the 40 megahertz of collisions that occur. We have to reduce that to about 1 or 1.5 kilohertz. So we have triggers of various kinds, and if you want to know more about them, ask Lauren. That perform this data reduction in real time. So this has to be done immediately. We can't yet farm it off all into computers. And once you require that all subdetectors are all working together well, that's typically about mid-90s% efficiency. So this is last year 93 to 95%, depending on exactly what subdetectors you needed. So this is sort of telling you we get about 3/4 of the data recorded that are used for most of our physics studies. Okay, so you might ask, what limits your ability to do this kind of science? Well, some things are just very rare. We don't get to control what happens in collisions because it's quantum mechanics. We have some probability. So things that just don't happen very often, or they can be very hard to distinguish from other things that are more common. So you have a game of statistics. You need to understand the detector. Many calibrations need to be done in situ because you don't actually have the full detector available to test with test beams. And things age, so you need to actually understand the performance of the detector while the detector is running. And the simulations are never perfect, so there's some mismatch between what we expect might happen and what actually does happen, and we have to account for that. And then there's also the fact that the theoretical predictions from perturbation theory, there's truncation uncertainties. We don't go to infinite order in perturbation theory. And there are many effects that are non-perturbative that we encapsulate in models, which we know aren't perfect. So those are also tuned, but also have uncertainties associated with them. So these are it's kind of a list of things that prevent us from seeing everything immediately. So we've done measurements of benchmark processes, so covering something like 10 orders of magnitude in production cross-section, production rate, from proton-proton to anything, to down here proton-proton to a pair of Z bosons. And these are measurements at different energies, the points, and the bands are theoretical predictions. And things look pretty good there. So at least we have some belief that we can have theoretical predictions for processes at the LHC. So a couple of things that we worked on at UT. So proton structure, you actually have to understand what's going on in these collisions. So one thing is say, well, you're colliding things inside the proton, so partons, quarks and gluons. So do you actually understand that behavior? Because that's one of the non-perturbative things I mentioned. So you can couple high-order perturbative calculations to the non-perturbative models of the proton structure itself and see whether they agree with data. So here we have data as recorded. Here we're looking at production of W bosons, W pluses, and looking at essentially the angle at which they're produced. And the data are the black points with the green uncertainty bars. And different models of the proton structure actually give us different bands here. So there's purplish and there's blue and all these other colors. And what that tells you is actually these things are systematically different from each other and we are able to constrain them. So one thing we found, in fact, was that expectations for the amount of strange quark in the proton were incompatible with data. And so once we included that, we found that we really had to raise our understanding of the fraction of the proton that is actually carrying strange quarks. And we're consistent with this being quite similar to the C quark contribution of up and down. Another thing we can ask is, well, how often when I collide these protons do I actually have two collisions? So normally we think of only one pair of things colliding and then producing stuff, but you could perfectly well have two different sets of things colliding. The fact that you have a proton collision in the first place means that there's other stuff in close proximity already, so you raise the probability of something else happening. And the reason this is interesting is because if you're looking for something rare where you produce X and Y, but you could actually just instead have one collision that produced X and another collision that produced Y, then you could have a actually quite common process mimic a very rare one. And so the way we looked for this, there's actually a bunch of analyses, but our particular one, we looked at the angular difference between X and Y. If they are produced in a single collision, you expect momentum to be conserved and they'll be back to back. If you have instead this double parton scattering, they should be uncorrelated with each other. And so we find, in fact, back to back. So this is pi difference between the angles, and then also some contribution that is quite consistent with this flat sort of uncorrelated bit. So Atlas has done a bunch of measurements, and what we see is actually consistent with models that have been proposed, but we really do need to understand these numbers a bit more. Okay, so moving on to the Higgs. So searching for the top Higgs coupling, which is a very hot topic. So what we're looking for here is top quarks emitting Higgs bosons. So this statement, I'll come back to it in a bit. CMS says that yes, they have seen it at 5 sigma. but okay. So what does that mean? That means a p-value less than 3 times 10 to the minus 7. So this is sort of our standard for observing things in our field. So we're trying to get a handle on this thing. So the search strategy here is determined by what the Higgs turns into. So the Higgs has a bunch of things it can decay into. Look at this vertical dotted line. This is the probability of various decays. So that would be the probability to BB bar. So here's 1. So that's like 50-something%. Then there's WW. Like that, and then there's various other modes. So actually mostly, I still do WW, as Lauren mentioned, for discovery I did WW, I still do WW, find it's the second most common mode, and it's quite useful. So we look at actually a whole bunch of modes. Not one single mode is going to give you an observation or not. You have to combine a whole bunch of different, you look at a whole bunch of different places, and all of them say, well, it's somewhat more consistent with Higgs being there than not being there. And then once you put them all together, they say, okay, well, you couldn't be wrong in all these different places at once. So the Higgs should be there. So in particular, my group worked on the trilepton signature. One of the problems with TTH, this TT bar plus Higgs production, is it's rare. So at design luminosity, you produce 1 in every 200 seconds. And then you're looking for a specific pattern of decay that is 0.7% of that. So if you were running at 100% duty cycle, you get only 3 of these produced per day, and then we actually are only able to find about 13% of them for various experimental reasons. So you see, you don't get very many of them. You have to run full out for quite a while in order to collect enough events to say you've seen something. But you expect certain patterns in the detector. So in this particular case, we've chosen to have 3 electrons or muons or some combination. We don't expect any correlation of whether they're electrons or muons. We expect 4 jets of hadrons. That's basically we have 4 quarks, and 2 of them are B quarks, so we expect to have that displaced vertex that I showed. And then there's various things arising from the angular momentum. You go and play with the Clebsch-Gordan coefficients, and you'll find that you expect that the leptons should be a pair of leptons should be close to each other. And then since you don't see the neutrinos, you have some momentum imbalance in the event. So there are some backgrounds. I won't go into them in great detail, but these are just other things that can happen. So instead of a Higgs, we have a Z boson or a photon. So that actually gives you the same kind of final state, except, okay, here you expect to see a peak at the Z mass for the mass of the leptons, and in fact we do. So we see this process, and we can normalize that process from data. We also have situations where a lepton comes out of a B decay, or a photon converts into an electron-positron pair. So this we have to determine directly from data through some complex things you can ask me about later. So since I would like to highlight the work of my student, instead of showing the normal analysis, I show the alternate analysis that we did. So this first paper on Run 2 data is public. In fact, we just got the notification it was published today. What we did in our case was, instead of running, so the nominal analysis uses very powerful multivariate analysis techniques. It runs boosted decision trees on boosted decision trees, and then foams everything in 5-dimensional space and all that good stuff. And it has good sensitivity. We actually get almost as good sensitivity by choosing 3 or 4 variables and then chopping things up in those. So if you are close to the screen, maybe you can actually see what the selections are. But the point is, as you go from left to right, the red part here, which is the expected contribution from TT bar Higgs production, grows. So we get a higher signal to background on the right, and you can see the data points are consistent with the adding the red, and they're less consistent if you take them out. So if you actually combine all these things together, none of the channels themselves, so again, these are a whole bunch of different decays that are looked at. None of them by itself is able to conclude anything super significant, but once you combine them all together, you get a measurement compared to the ratio to the standard model of 1.6 plus 0.5 minus 0.4. Okay, so that's still not statistically significant by our standard, but it's getting there. If you then take that and combine that with other measurements that were made, what you find combined is 4.2 sigma. So again, on this thing, it's Not observation, but very good. And we expect 3.8, so that's telling us it's consistent with, we're not somehow giving a much stronger evidence than we would expect to for the standard model. So if you combine everything, it's 1.2 times the standard model plus or minus 0.3, so perfectly compatible with standard model. If you look at the systematic uncertainties, at this point we're really worried about how good our measurement is, and not just whether we can see it or not. You find that quite a few of these are actually theory uncertainties. So we have significant experimental uncertainties as well, but we do need to basically understand some of the theoretical modeling of these backgrounds and the cross-sections for that. So here's the asterisk. Yesterday, CMS put out a claim of a 5+ sigma observation, and you can ask me about that later. Okay, so going back, so we haven't actually repeated this exercise, but we did it for run 1. For earlier data, you can combine all the different Higgs analyses together and parameterize the Higgs interactions in different ways, and do this comprehensive analysis, see how much you scale the standard model couplings by, how much you're allowed to scale them by. And if you look at the top Higgs interaction, which is this row here, we are combined Atlas and CMS results, compatible. We were compatible at 2 sigma. We're going to be much more compatible with the standard model now because both of us have measured stuff compatible with it now. But this is actually, you're able to pick apart couplings to Z bosons, W bosons, top, tau, B, gluon. So this is actually, and you can even say that the undetected decay fraction is less than 34%. So we're not missing more than a third of Higgs decays. But the point is that really there's still a lot of room for modifications. This is a very large scale, and so you can easily sneak 10% in there, and that's quite reasonable discrepancy, and we would not have seen it yet. 20% easy. Okay, so a brief thing about these flavor-changing neutral currents. So as these aren't, in fact, in the standard model, they're at an extremely small rate, 10 to the minus 15, I think. So you're just not going to see them. But if you have more complex Higgs sectors than just the one of the standard model, you could in fact you could create this coupling. So this would cause the top quark to decay into a charm quark and a Higgs boson, so we can go look for that. So we've done that. We actually reinterpreted the results that I showed earlier, with trilepton and 2 lepton events. And what we found was consistent with no signal, but also consistent with some signal. So this is something to look at again. And I will just say there's actually updates for run 2, and we have a paper that should be coming out very, very soon on this, so stay tuned. Okay, so future, so just a few things on the LHC program. So we're currently near the design energy. We don't expect any massive increases of the energy in the near future. So we'd like to go to the design, which is 14 TeV. We already surpassed the design luminosity, so that's good. Although the design luminosity was only ever a stepping stone, we expect it to do better. So through the mid-2030s, the plan is basically that you have luminosity increases. This is a bit out of date. So this actually, somehow I didn't get the latest version of this slide. So this actually is now 30 times because we took enough data last year. So we're going to get, we need major accelerator detector upgrades for this, and lots of people are involved with those. And after that, perhaps we get an energy increase with stronger magnets. Who knows? So this is going way off the end of this chart in terms of plan. So it's not just accelerator, you collect more data, just run things and do things the way you've always done them. There are lots of improvements of other kinds to come, in particular analysis techniques. So we've actually had very fruitful collaborations between theory and experiment for this. Generally, I think final LHC results are probably better than we currently predict because we'll just be better at doing analyses. So there are a whole bunch of ideas that people are working on to improve sensitivity, to do better, to reduce systematics. My group has some interest in the non-shaded things. So some new opportunities, as I mentioned, the top mass and the top Yukawa coupling are intimately related. So we can also do top mass measurements. As you get more data, you can try and use different techniques. So this is one that we've been studying here. For people in the know, it's using J size as a proxy for B jets. But by collecting lots of data, you can determine the difference between this red Gaussian-ish thing and this blue Gaussian-ish thing, and that corresponds to 5 GeV difference in the top mass. But the point is we can actually get, this is really statistics limited, and by the end of this year, we're actually going to be competitive statistically with some other normal measurements of the top mass. So this is something, again, it's enabled by taking more data. For far future, LHC is really the only place we're going to be able to study top Higgs interactions for a long time. There are many statistically limited topics, even with HLLHC. In the 2030s, we might get new colliders that can improve, give us better measurements. So for example, if we have this thing called the International Linear Collider, we can imagine reducing the top mass uncertainty down to 40 MeV, so over an order of magnitude improvement, which would be great. So here, from the Japanese effort on this, is a celebrity and Lynn Evans, who is head of the ILC project. So here are a bunch of people that I've had the privilege to work with doing this research. And here is a place in Texas. So thanks for your attention.
Yeah, so you mentioned two mild discrepancies with the standard model. One was the CSEA quarks, the strange quarks being more. So I wondered what we learned about QCD. Did that feed back into lattice QCD? Because why didn't
Yeah, okay, so that's a good question. So you're talking about this, I assume. So the issue here is, as far as I know, and someone who knows more about lattice can correct me, and the problem is you're dealing with details of proton, of protons at rest, and this is very difficult to do. So I don't think there's actually ab initio predictions of what this ought to be. So it's basically been assumed done in fits to earlier data sets which had significantly more uncertainties, that you would have less strange, that it's heavier, therefore there's a strange suppression, and some numbers got put in as baselines, but they've never really been tested again with the data we have now. The problem is that these things, they have physics in them, but they always start off from some model that you put in of what the densities are, and if that initial model is wrong, all the extra physics you do to it will not fix it.
This was not amenable to lattice?
I don't believe so, no. This is really, you have to go look at it in data.
More the FCNC stuff at the beginning?
That
small discrepancy?
The flavor violation, yeah. Flavor, yeah. So universality violation.
And what theories would it descend from if it is real?
Okay, so the easiest way, so one thing is just to put in this Higgs, this charged Higgs. So if you have more than one, you have a more complicated Higgs sector than just one doublet like we have in the standard model, then naturally you'll get an object out like this, and it will interact differently with taus and with mu's and with electrons, unlike the W. So you could introduce that and it would change this interaction. The problem is, it turns out that this is incompatible with other things. So the favorite explanation, I believe, at this point is leptoquarks. Essentially turn it on its side and turn this interaction on its side, yeah.
How do you do the simulations? It seems like you need in excess of 100 or 128 bits of precision to get any reasonable accuracy after your first order cancellation.
Well, so theorists are very good at coming up with ways to hide those large numbers. So you don't actually wind up with, once you've lived with this, then you do the cancellation from the beginning, and then you don't have these gigantically large numbers appearing in your actual calculation, so you're safe there. But yes, it's, so this is more of a conceptual thing than an actual impediment to calculating. The rest of it, precision is, we don't usually have precision problems per se, but we do have lots of fun things where people, overflow counters without expecting it because they didn't really think about it. So,
Can you comment on the latest CMS
Sure. Okay. So the latest so the result that we have that I showed here is using only the 13 TeV data of the 2015-2016 data, and so we're adding 2017, obviously. So we also had earlier data at 7 and 8 TeV, which we did the analysis on. So in that case, we wound up with actually a fairly significant excess over the standard model. I mean, not significant statistically, but it was large. So what we knew was if we combined this result with the earlier result, we would actually get a very large number here with not much improvement on the expected, because the earlier data really was worth much less than the data we're taking in terms of what you would expect to get out of it. But because we had an upward fluctuation there, we believe it was an upward fluctuation, we would be sort of claiming 5 sigma, even though we didn't expect the experiment to do that well. So CMS's run 2 results are essentially the same as ours. They also had an upward fluctuation in run 1. And so their claim of observation is precisely that they combined the 2 data sets, but in that case, they're taking advantage of the fact that they already had what in this assumption must then have been an upward fluctuation in the earlier data. So it's a little bit, at that point, it becomes a philosophical argument of what is 5 sigma, which, whatever. So I think we can say we've seen it, but okay, it's a who got to 5 sigma first? No. Yeah, the expected is 4.2. So they had a significant effect. And the problem is, say that there was some correlated effect that was visible in run 1 data for both ATLAS and CMS and got swamped by stuff in run 2, then we might have been mistaking something else for TTH in run 1. In run 2, we've seen TTH. So when you're doing that combination, you might actually be calling extra significance for TTH production something which in fact was some other process, and that would be unfortunate. But again, it's a bit of a philosophical argument.
More questions? I wanted to ask about the double proton scattering measurement. That's of course a very nice measurement. I want to think it's like nice you can do it at the LHC. So
to be fair, this is the least powerful way of doing it, but
so where does double proton scattering get important in terms of being a background to another process you'd want to measure?
So one of the famous issues is same sign W production. So if you produce W plus or W minus, so then you've got you don't have total charge 0, which, okay, so you have to arrange for some interesting initial states to get that to happen. So that's quite rare in the standard model and could be used as a probe of how the W bosons interact with the Higgs field and with each other. The problem is that you could produce 2 W bosons in different scatterings with the same sign, and so it's believed that similar kind of kinematic effects here, that they just don't quite look the same, allow you to select for W plus produced like this instead of like this. So they're actually not so worried about it now, but they realized, oh no, actually this might be something we have to worry about. And just in general, if you're really doing rare studies, you should actually at least stop and ask yourself whether this could happen. Certainly when we started this particular analysis with this W and a J psi, we didn't expect this to, we did the calculation, we said, oh, actually, this is something like a third of our signal. We didn't expect that. Actually, we expected 0. So the fact that we saw anything here at all was actually very interesting. But then, okay, on top of that, we saw this contribution. So.
Very nice. Are there any other questions? All right, not thank you.
Thanks again.
Very nice summary.
Thank you. I don't know